Welcome back. In the last couple of sessions, we talked about ensemble learning. We gave an introduction of the landscape of this exciting ensemble machine learning methods, and we went on to illustrating the bagging methods with decision trees as well as bagging, and went on to look at random forests as well as extra trees. In this session, we're going to go into a different type of ensemble learning, which is boosting. Also called boosting, hypothesis boosting. The basic idea is that you combine several weak learners into a stronger learner, and you train your predictors in a sequential manner. Okay, so it's actually in a serial manner. All right, there are a couple of links that I've provided here from the actual creator himself, Robert, and also Wikipedia and a few other resources for you to look at. Now, AdaBoost is actually fairly recent. It's in 1995 that it was created. Still around 23 years of technology here, or 23-year-old technology, but it's actually one of the very popular machine learning algorithm that's used until fairly recently. Now, the basic idea of AdaBoost, also called adaptive boosting, is that very similar to human learning, the algo learns from the past mistakes by focusing more on difficult problems it did not get right in prior learning. So basically, the actual whole idea here is that it mimics the human being. So you make mistakes, all right, that's fine. So we focus on the areas that we made mistakes on and just keep learning that and spend more time on that. Whereas those that we got right, we're gonna put less weight to it. So in machine learning speak, it pays more attention to training instances that previously underfitted. Now here's a source from scikit-learn, the definition of it in terms of a pseudocode in a sense. Basically, you fit a sequence of weak learners, basically models that are only slightly better than random guessing, such as small decision trees, on repeatedly modified versions of the data. The predictions from all of them are then combined through a weighted majority or sum to produce the final predictions. Now, the next step then is that the data modifications at each so-called boosting iterations consists of applying weights to each of the training samples. Initially, those weights are all set to equal. All right, that's why it's 1/n, equal weightage, so that the first step simply trains a weaker or weak learner on the original data. However, for each successive iteration, the sample weights are individually modified and the learning algorithm is reapplied to the reweighted data. So there is actually a shift in the weightage now. And how does it actually shift this weightage? So at each given step, these training samples that were incorrectly predicted by the boosted model induced at the previous step have their weights increased, whereas weights are decreased for those that were predicted correctly. So we increased the weight for those that we got wrong, we decreased the weight for those that we got right. So basically, as the iterations proceed, examples that are difficult to predict receive ever increasing influence. Each subsequent weak learner is thereby forced to concentrate on the examples that are missed by the previous ones in the sequence. Now that you understand the actual basic idea of AdaBoost, let's look at some codes. Again, I've prepared the Titanic data, we're leaving that part there, and we've already left the train test splitting here. I'm just going to change that to 0.3. Again, we have the performance measurement matrix as well as the training as well as the test scores prepared for as before. So scikit-learn ensemble, we're going to import AdaBoost classifier, and okay, so Ada. So let's just instantiate this Ada classifier. And we just need to fit this to the training data, X train and Y train. All right, okay, what does this mean? Okay, so let me just copy these notes that I've prepared earlier. The semi-16, which is this one here, basically means stage-wise additive modeling using a multi-class exponential loss function, and R here stands for real. So this is the algorithm that the edibles actually make use of. And now you can read more about this by the link that I've provided here. It is actually a PDF or a paper that's actually published by Stanford called Multi-Class Edibles. And that's really the original paper that published this. So let me close that off and move on. Now let's have a look at the actual performance, print score. Again, I'm going to come up here and copy this portion without the colon. We're going to need to open the bracket, and we do need to actually enter the classifier. All right, we have double brackets, so let's just print that. Okay, right, that was fast. So you have the accuracy score is 8661. Let's recall here in terms of the decision tree. What do we have? Okay, this is a decision tree, and in sample under the train score, the decision tree got a score of 9528. Okay, so it's better than this. The average accuracy score is 7333, and the standard deviation is 0.07. So 7724 versus 733. So in terms of the average accuracy, decision tree outperform. In terms of the standard deviation, edibles actually has about 50% less. Well, not quite, about 40% less. So let's have a look at the score now. This time we're going to look at it. I'm just going to copy this for test score. Let's see how it performs out of sample. Okay, so it's within the range of our average accuracy. And how does it compare 7636? So it's exactly the same. Again, I won't re-emphasize what I already said. That's pretty much what I want to actually cover in terms of the edibles. We will revisit edibles in a separate setting with a different data set. But there's just one thing that I do want to stress here is that the edibles here is actually edibles on the base estimator, or those states none here is actually decision tree. Now the beauty of edibles is that you don't actually just have to do this on decision tree. You can actually change it to another classifier. So let me just vary this a little bit, and we're going to do edibles with random forest, just so that you don't take my word for it. You can actually see that it can indeed be done. So from sklearn ensemble, we're going to import random forest classifier. Okay, and edda classifier is equal to edda boost classifier, and we're going to random forest within it. Okay, and we need to fit the edda boost to the X train and also Y train. And here you have the base estimator now is changed to random forest classifier. Also, let's have a look, see if this is any better than before. I think these are all the same, so we just need to copy this so that saves time. And let's have a look at the actual performance. It's going to take a while longer because remember we have two layers. We have the random forest layer as well as the edda boost layer. So 7256 still does not perform as well in terms of the accuracy. Standard deviation is still better than decision tree. Decision tree, as we know, does actually have a high variance, and that's pretty much what we expected. This is out of sample 7818. Finally, it outperformed the decision tree out of sample, and that's actually the first algorithm that performed better out of sample. Although in sample the actual accuracy was not as good as the decision tree itself. At least right now we've gone one step further and been able to actually expand on the repertoire that we have with a good understanding of edda boost. And what I'd like you to do for the remaining videos, I'd like you to actually make use of what we actually did do within the random forest lesson. Recall that under the random forest lesson, we actually did the grid search. And within the grid search, we actually did, where is the, okay, this is the best estimator in terms of the parameters. You might like to actually extract some of these in terms of, could be the number estimator, could be the minimum samples split, and apply it into the random forest itself. Basically specify it here in this line and run it and have a look at whether you are able to actually improve the performance or not. The part that actually does matter quite a fair bit is actually a number estimator. So you might want to increase that instead of 50 on the edible side to 1,000. Again, increase the random forest to 1,000, number estimator to 1,000, and see how it actually impact on the score. So let's pause the video, and when you come back, I'll review my answer, and so that you see you can compare mine against yours, and we'll wrap up the lesson after that. Well, I hope you gave it a try, and you probably discovered that it takes a long time to run those parameters. I tried it. I wasn't able to do it in the last hour or so. Looks like with this, you basically need to run it overnight and over a few days. And we're starting to actually get to the cutting edge of machine learning algorithm. And boosting is one of those that does take quite some time. And as you actually start getting into this space, you realize that the waiting time is quite long. And just giving you a heads up, and quite often this is what you will experience. But I wasn't expecting it to be that long. Nevertheless, I hope you actually have at least give that an attempt. If you're gonna run this, you might have to switch it on and go to work, and then come back a couple of days later, have a look at it. In any case, that's really the end of this lesson, and what we really have covered here is edibles, and just pure edibles with classification tree, and also edibles with random forest. And that's the really interesting part about edibles, is that you can actually fit other classifier into it. And when we come back, we're gonna start going into gradient boosting machine. I'm looking forward to it. I look forward to seeing you in the next video.